I do energy lab? I have cart, I have track, I have a scale. So what I want you to find out, and of course the cart has a spring, right? So when you compress the spring, right, then this spring will push against this wall, right? So the spring potential energy is going to become kinetic energy, and eventually is going to become the gravitational potential energy. That's what you're going to find, gravitational potential energy over here. So location A, location B, location C, right? So lots of unknowns, you're going to have to also find the K, the spring constant. So the first thing first, I want to measure the cart. The cart is 264.17 gram. Our goal is to see where the velocity is 0. Take a look. I'm going to take this one, make sure this doesn't go off the track and skid. All right, so 84. So the first trial I see at 84 is velocity, final velocity is 0. So the height is exactly 6 centimeter, right? 2.5 centimeter, right? Diagram. As you see that you have a box with a spring. Let's say the spring at rest 5 centimeter actually. When the spring is stressed, let's say this is X final is 7.5 centimeter, and when it is compressed, then let's say X final also 2.5 centimeter, right? So there is a wall, right? That the box, the spring is compressed against this wall, right? Sure. This box is mass is mass is, let's say 264 gram. Now we want to know this spring, size of this spring. So the size of this spring is, we're going to call delta X, which is of course X. No, this is not stress, this is compressed. So this scenario we're going to use XF minus XI, which is 5 centimeter minus 2.5 centimeter is equal to 2.5 centimeter. All right, and that divided by 100. So the delta X is 0.025 meters. Okay, so that's this spring, right? Now, if you let the spring go, right? Okay, let's say there is a button over here. You press it, you let the spring go, and the spring gonna come to its natural state, which is X initially is 5 centimeter. Then this box will start moving up the ramp, and let's say this is location B, this is location B, and let's say this is location A, right? I'm going to use different color for different location. This is location B, right? And this is location A, right? And this is, let's say this is location B, right? And this height is, let's say 0.06 meter, right? Okay. And the ramp is, let's say 0.84 meter, right? Okay. And let's call this one location B, right? Location C. At location C, you have also mechanical energy, right? Okay. So you have a mechanical energy over here at location A. You have mechanical energy at location B. You have mechanical energy at location C, which is half the distance between, well, I'll give you the distance, 0.03 meter. And mechanical energy at location B. Right, mechanical energy at location A is half kx squared, and mechanical energy at location mv square. Look, mechanical energy at location C is half mv square plus mgh, and mechanical energy at location D is just mgh. Alright, so mechanical energy at location A has to be equal to this one has to be equal to this one has to be, because the conservation of energy. Now, the first thing you're gonna find is the angle, right? You're gonna find this angle. We can use saw, right? Car, TOA, right? We cannot use TOA because we don't have JSON. We cannot use car because we don't have JSON, but we can use saw, sine. Sine theta is opposite 0.06, and the hypotenuse is 0.84. So theta is equal to sine inverse 0.06 over 0.84, and that 4.1. So 4.1 degree. Okay, that's problem number 1. Problem number 2, we're gonna find, in this case, no friction. Okay, so the problem number 2, we're gonna find the acceleration. Acceleration if there is no friction. G sine theta 9.8. Oh, by the way, negative 9.8. Sine 4.1. So this is negative 0.7. So acceleration is negative 0.7. So I'm going to draw this ramp again over here, just to show acceleration of the box at different location. So the box is, let's draw the box. Okay, the box is here. So the box is here at 3 locations I'm going to draw, and the box is here, right? So acceleration is this direction. I'm going to use the different color. So acceleration is this direction, and this is 0.7 meter per second square. Acceleration is this direction at 0.7 meter per second square. Acceleration is this direction, 0.7 meter per second square. So acceleration is constant. Okay, good. The best way would be to have the same size. I'm going to take this one here. To have the same size, I'm going to take this one over here. So I don't have to write this 3 times. Good. There's the acceleration. Okay, now let's find the velocity. Okay, so the velocity you're going to find 2 ways: kinematics and then the energy. You're going to find the velocity right here. So let's say velocity right here. And this is the acceleration. So acceleration, let's put it on the top. Acceleration. We're going to find this is acceleration, this is acceleration. We're going to find the velocity, right? Velocity has to be this way. Okay, so velocity we are trying to find. So the velocity is Vf squared is equal to Vi squared plus 2AD, right? So Vd squared at location D, this is location D, is equal to Vd squared, because we're going to find the velocity right here, plus 2AD, right? So this is 0. So velocity is at location B 2AD, right? So velocity is 2 times A is, we already found that, 0.7, and D is of course 0.84. So velocity is 1.08. We're gonna use the energy, and then mechanical energy at location D is equal to mechanical energy at location D. So V is half mv squared and D is mgh, right? And cancel. V is equal to 2gh. V is equal to 2, G is equal to 9.8, and H is equal to 0.06. Now notice that here we use 9.8, and here we use 0.7. Here we use 0.06, and here we use 0.08. Please make sure you understand this why we have to use 9.8 and why we have to use 0.7. So both give you 0.08, 1.08. So we're gonna go ahead and write velocity is 9.08 meter per second. And by the way, the velocity is not going to be 1.08 because the velocity will be 0 over here. Okay. It's because the velocity and acceleration are the different direction. Okay, good. So now, what we're going to do is we're going to find out we're going to find out velocity right here. Great. So the velocity right there is we can use half mechanical energy at C is equal to mechanical energy at D. So half mv squared plus mgh is equal to mgh. Notice that I have to write C over here because this is C. I have to write D over here because this is D. M cancel. So you have velocity is equal to square root of 2g delta h, right? So velocity is 9.8. What is delta h? Delta h is hd minus hc. hd is 0.06, h is 0.03. So 0.03. So velocity is 0.77, I don't know. So let's see. The square root of 2 times 9.8 times 0.03 is 0.77. Okay, so that's exactly what we expected. We expected velocity is getting smaller. So velocity is 0.77 over there. Okay, good. And that's why velocity is 0 over there. Okay, good. We are making progress. Now we're going to find the k. So remember this is half kx squared, right? To find the k, we're going to say mechanical energy at location A is equal to mechanical energy at location B. Half kx squared is equal to half mv squared, right? Half cancel. K is mv squared over x squared, right? N is 0.264 times v is, of course, at this location, the v is 1.0608 squared, and at this this is delta x is 0.025 squared. So k is 493 Newton meter, right? So the k is, what is the k? K is 493 Newton meter. Okay, good. Now that we found k, what is the next thing we're going to have to find? We're going to have to find ME at our location. So we're going to find the mechanical energy at our location. So let's first find the location 1. So the location 1 is half kx squared, right? So half kx squared. So half k is 493 and x is 0.25 squared. Alright, and then we're going to find this one, mechanical energy at location D is half mv squared, and that is half 0.264, and v is 1.08 squared, right? And this one, this is wrong. X is actually 0.025 squared, right? So this is how much? This is 0.15 joule, and this is how much? This is also 0.15 joule. Now we're going to find this one, mechanical energy right here. Mechanical energy right here is half, m is 0.264, b is at location 2, b is 0.77 squared, plus m is 0.264, g is 9.8, and h is 0.03. So mechanical energy at location C is also 0.15 joule. Now at location D, mechanical energy at location D right here is m is how much? 0.264, g is 9.8, and h is 0.06, so 0.15 joule. So mechanical energy is same. Okay, good. So what is the next question we have to do? We have to find the gravitational force parallel to the ram. So mechanical energy. So mechanical energy over here is, let's write it down. Mechanical energy over here is 0.15 joule, and over there is also 0.15 joule, and over there is also 0.15 joule, and over there also 0.15 joule, right? Okay, so as you see, conservation of energy hold because there is no friction. Okay, good. Now let's find the gravitational force parallel to the ramp, mg sine theta. So m is 0.264, 9.8 sine 4.1. So how much is that? 0.18 joule, right? Okay, so gravitational force to the ramp. So I'm going to draw this one again. Alright, so I'm going to put this box over here now. So the gravitational force is 0.1, right? Okay, good. Now the next thing we want to do is find the acceleration. So acceleration by Newton's second law, so F equal to ma, right? So A is equal to F net over n. There is no other forces. This is the only net force. So we're going to use 0.18. By the way, this is negative. This is negative. Why this is negative? Because F net is this direction, so this is negative. You can see this was negative when I calculated it. So this is negative 9.8, so this is negative, okay? So this is negative, so make no mistake with that, okay? So F equal to ma, so make sure this is negative, you understand it, okay? So A is F net over m. So F net is 0.18 negative and m is 0.264. So acceleration is negative 0.7 meter per second squared. And that's what we found before, negative. Okay, so we understand that acceleration is at the same direction as the net force. Acceleration is same direction as the net force. Okay, good. Now we're going to quickly write this is acceleration, and acceleration is 0.7, right? Acceleration is 0.7 meter per second squared. Okay, now work done by, so work done by is F d cosine theta or kx squared half kx squared, right? So W is equal to half 493, right? 493, x is how much? 0.025 square, right? So work done is how much? Let's see, 0.15 joule, right? You can also use this formula. Let's use this formula also. Let's see whether we get the same thing. W is Fg parallel d. Fg parallel is how much? Fg parallel is Fg parallel is over there 0.18. D is 0.84. 0.18 times 0.84. 0.18 times 0.84 is 0.15. So work done is 0.15. Okay, good. So work done by spring is 0.15. Good. Now let's put friction on it. Let's say the friction is 0.01, right? Okay, now let's find the force of friction. This one will be a little bit more challenging, so please pay attention. Force of friction. So I'm going to write force of friction is equal to what? Is equal to mu k mg cosine theta, right? So force of friction is 0.01, m is 0.264, g is 9.8, and then cosine 4.1, right? Degree. So FF is, make sure you put negative over here, negative 9.8, otherwise it's not done. 0.01 times 0.264 times 9.8 times cosine 4.1, and that is negative 0.0258. Okay, so force of friction, I'm going to just write force of friction. I'm not going to write acceleration. I don't need acceleration right now. So I'm going to just write force of friction. Force of friction on this box is, force of friction is this direction. Force of friction on this box is how much? Force of friction is 0.026. 0.026. Okay, good. Now let's find the FG parallel. FG parallel is this, and the box is now trying to move this way, right? Okay, so now as you know that the lamp is started right here, right? The lamp is started right here, the B, location B, and this is location A, right? And then the box is right here, and against A is B. So the over here, what is over here at B, at A there is F is equal to Kx, and also P is equal to half Kx squared. But at B, there is no half Kx squared, or there is no half Kx. So at B, the force is there is no force there. Force is 0, right? By the time it gets to B, right? There is no force. So the only force we're going to write F is equal to ma, right? So only we have two force. The force is negative 0.18 Newton minus 0.026, right? Plus you add them up, ma. Okay. So negative 0.18 minus 0.026 is equal to ma, right? So 0.18 plus 0.026 is equal to acceleration is negative 0.206 divided by 0.264 and that is 0.8. Acceleration is negative 0.8, right? 0.8. Yeah, that makes sense, right? Why that makes sense? So before we got what acceleration is, before acceleration was right this way. Acceleration was negative 0.7 meter per second squared. Now acceleration is negative 0.8 meter per second squared. Now that makes sense, right? Since there is a friction, there will be more. Then the motion will be slower than if the velocity is 0.77 over here, right? With the friction, velocity gonna be less than 0.77. Why? Because the deceleration is bigger, right? Okay, the object is slowing down. Two forces against the object. One is this one, and one is this one. Two forces. So object is fighting with the two forces. So acceleration is the magnitude of acceleration is bigger, but the acceleration is smaller than before.